In this video, I will present our Micro 2020 paper, MDM, the GPU Memory Divergence Model. It's a collaboration work from Ghent University, Norway University of Science and Technology, as well as Huawei. First, I will introduce state-of-the-art GPU performance analysis tools. Analyzing and optimizing GPU architecture for the broad diversity of modern-day GPU compute applications is challenging. Simulation such as GPGPU sim is arguably the most commonly used evaluation tool since it enables detailed, even cycle-accurate analysis. However, it is slow and the parameter sweeps commonly requires thousands of CPU hours. Moreover, it provides limited insight. Machine learning-based model requires offline training to infer or learn a performance model. The training is slow for machine learning-based model. Although it is accurate, extracting insight from a machine learning performance model is not straightforward. For instance, a machine learning-based model is a black box approach with limited insight. An alternative is analytical model such as GPU-MAG, which captures the performance-related behavior through a set of equations and provides more insight. GPU-MAG is fast but inaccurate. In this paper, we propose memory divergence model, which is both fast, more accurate, and providing more insight. Next, we point out the prevalence of memory divergent GPU applications. We define an application as memory divergent as it features more than 10 divergent loads per kilo instruction. In particular, a divergent load will generate multiple catch line accesses. We use NVIDIA's Virial Profiler tool to categorize several benchmarks, including Rodina, Parallelism, and find that 38% of the benchmarks are memory divergent. These applications typically have strided or data-dependent access patterns. Although memory divergent applications are prevalent, state-of-the-art analytical model such as GPU-MAG is inaccurate for memory divergent applications, which incurs an average 298% performance prediction error. In this paper, we propose memory divergence model, which captures the key performance behavior of memory divergent applications. Now, we introduce the model framework. The first task is to collect traces, which can be accomplished through instrumentation or through functional simulation. Next, we use the instruction trees to create interval profiles for all warps and select a representative warp as the input of the performance model. At the same time, we feed the memory traces into a catch simulator to obtain the miss rate. Finally, we provide the intervals and miss rates to the performance model and predict the overall performance. The timing overhead of MDM can be divided into one-time cost and recurring cost. One-time cost occurs per application, including trace collection and representative warp selection. In contrast, recurring cost is proportional to the number of the architectural configurations. It includes the catch simulation as well as the model prediction. The recurring cost is much less than one-time cost for one design space. We find that MDM model dramatically reduces the evaluation time compared to simulation by 65x for one design point. This speeds up further increases with more architectural configurations. Instrumentation-based trace collection is also 6.1x faster than using functional simulation. This kernel squares the contents of an array and reorganizes it into a metric. In particular, the access pattern strides are determined by GS. If GS equals to 1, threads in the same warp will access one catch line. It's the case of non-memory divergent. In contrast, if GS equals to 32, the kernel becomes memory divergent because threads in the same warp go to different catch lines. In order to understand the key insight in MDM model, we compare non-memory divergent applications and memory divergent applications. First, I will use an example to show the thread-level parallelism in non-memory divergent applications. In non-memory divergent applications, each warp generates one cache line access. Warp 1 issues a compute instruction and then a long latency memory instruction, for instance, one L1 miss. Then the SM chooses another warp, for instance, warp 2, and executes the compute instruction in warp 2. After that, warp 2 also generates a long latency memory access. Warp 3 to warp 5 follow a similar way. When the memory instruction is finished, the compute instruction is executed. From the SM side, the long memory access latency can be hidden by running other warps on the same SM. Hence, there is no store. However, the thread-level parallelism breaks down in memory divergent applications. In memory divergent applications, threads within a warp will access different cache lines and the core will run out of MS chars. Warp 1 issues compute instruction and a long latency memory instruction which leads to MS char full. Then warp 2 issues compute instruction. The memory instruction in warp 2 cannot be issued until MS char is available. Warp 3 through warp 5 follow a similar manner. In particular, different from non-memory divergent applications, memory accesses from different warps cannot be generated in parallel due to limited MS char resources. On the SM side, there is significant store. Hence, frequent MS char stores limited the ability to hide memory access latency through thread-level parallelism for memory divergent applications. This figure shows L1 miss latency breakdown for selected GPU compute applications. We observe that delays due to insufficient MS chars as well as queuing delays in the NOC and DRAM subsystem are significant in memory divergent applications, while non-memory divergent applications are hardly affected. Hence, the key insight in MDM model is that the poor spatial locality in memory divergent applications cripples the latency hiding through thread-level parallelism in GPUs. We also made two observations for memory divergent applications. First, flood of memory requests leads to widespread cache blocking due to lack of available MS chars. It also causes widespread congestion in NOC and DRAM. Now we explain how MDM model captures these observations. This equation shows the way to calculate per SMIPC. Particularly, this part equals to the total cycles without any contention, which can be obtained through GPU-Mac model. This part equals to number of instructions per warp. W equals to the number of warps per SM. The problem is how to get the store on MS char, NOC, and DRAM, which is also the key component in MDM model. The overall IPC is then calculated by multiplying with the number of SMs. We find the per MS char utilization in memory divergent applications result in issuing requests in batches, and that each batch contains as many requests as there are MS chars. We call it batching behavior. It's described in this equation. MS char store is calculated through multiplying number of batches minus 1 and the length of each batch. We then combine L0 contention with average store cycles due to queuing in the NOC and DRAM subsystem to obtain S memory. We now describe how MDM formalizes the memory contention model. In a real GPU, memory contention occurs because the memory requests of all SMs queue up in the NOC and DRAM subsystem. For MD intervals, latency hiding breaks down and the kernel is exposed to the complete latency. As shown in this equation, number of SMs multiples M equals to the total requests in the NOC queue. L NOC service equals to the service latency of each request. The equation for M is shown below. In particular, the number of read requests on each SM is bounded by number of MS-char entries, while the write request can bypass MS-chars. We use the similar mechanisms to model DRAM queuing delays. We compare MDM both with cycle-accurate GPU simulation and real hardware NVIDIA GTX 1080. In order to collect trees, we extend the n-bit binary instrumentation framework. As for workloads, we select 17 applications, 8 non-memory divergent applications and 9 memory divergent applications to evaluate MDM. This table shows the simulated GPU configuration. We assume 28 SMs, 64 warps per SM, 128 MS-chars per L1 cache, 1050 GB per second NOC bandwidth, and 480 GB per second DRAM bandwidth. We will conduct the sensitivity analysis for important parameters such as SMs, number of MS-char entries, NOC bandwidth, as well as DRAM bandwidth. In order to evaluate MDM model and show the source of prediction improvement, we evaluate several performance models. The basic model is GPU-Mac. We enhance GPU-Mac minimally by taking into account the NOC queuing and call it GPU-Mac Plus. MDM-Q improves GPU-Mac Plus by using MDM's memory contention model. MDM MS-char improves GPU-Mac Plus by considering MDM MS-char batching model. MDM model is a final model which includes both memory contention model and batching model. This figure shows the IPC prediction error for non-memory divergent applications and memory divergent applications under different performance models. MDM significantly reduces the prediction error for the memory divergent applications by 16.5x compared to GPU-Mac. Across all benchmarks, MDM reduces the prediction error to 13.9% on average. Now, report model accuracy across DRAM bandwidth configurations. GPU-Mac's prediction error increased with DRAM bandwidth. Increasing DRAM bandwidth puts increased pressure on NOC bandwidth, which GPU-Mac does not model. GPU-Mac Plus models the NOC queuing delay and the corresponding L1 mid-store cycles, which significantly decreases the prediction error. MDM-Q and MDM-MS-char further improve accuracy through improved queuing and MS-char models. However, prediction error still increases with DRAM bandwidth. MDM counters this trend by synergistically modeling saturation and batching behavior. We also demonstrate that MDM provides high accuracy when we vary the number of MS-chars, NOC bandwidth, as well as SM count. The streaming cache, as proposed in NVIDIA Volta GPU, is interesting because it adds a large number of MS-chars to each L1 cache. For instance, 4,096 MS-chars in this case study, and adopts an on-field line allocation policy. We find that MDM performs equally well for streaming L1 cache. It improves prediction accuracy by 8.66x compared to GPU-Mac. Streaming cache practically removes L1 blocking, but the batching behavior still occurs because the queuing in the NOC and can only buffer a finite number of concurrent requests. Now, we move to real hardware validation. The first board is GPU Mac with function simulation to collect trace. The second board is GPU Mac with instrumentation. Binary instrumentation improves the accuracy of GPU Mac from 260% to 164%. The reason is that profiling happens at the native instruction level using instrumentation instead of intermediate PTX level using functional simulation. Then, MDM significantly reduces the prediction error to 40% compared to real hardware. Case studies are important for a performance model. The most obvious use case for the MDM model is to drive design space exploration. In this figure, we report the performance results as a function of SM count and DRAM bandwidth for a non-memory divergent application, BT. All results are normalized to simulation with 28 SM and 480 GB per second memory bandwidth. We find both GPU Mac and MDM can capture the performance trend for non-memory divergent applications. However, it's not the case for memory divergent applications. As shown in this figure, GPU Mac overpredicts the performance speed up with more SM and memory bandwidth. In contrast, MDM can capture the performance trend accurately. Another use case for MDM model is to predict the relative performance at a different clock frequency. For general purpose models such as GPU Mac and MDM, we predict performance at both 1.4 GHz and 2 GHz and compare the performance difference. In contrast, for special purpose models such as CRISP, we first run at 2 GHz and then predict performance at 1.4 GHz. This figure shows the prediction error for predicting the relative performance at 1.4 GHz versus 2 GHz for memory divergent applications. We find that MDM achieves similar accuracy as a special purpose CRISP model. Overall, MDM model improves the performance prediction accuracy by 16.5x for memory divergent applications. It is also 6.1x faster by using instrumentation-based trace collection compared to functional simulation. Moreover, it has multiple case studies, such as design exploration, DVFS, and streaming at one cache. We also provide an open source implementation of MDM